Hello, and a very nice welcome to today's webinar. This is the next entry in our webinar series, and today we are going to talk about the time-dependent analysis. My name is Jan Ostersch, and I'm a technical consultant at the Alpine Infrastructure Competence Center in Graz, and I will be your host for today. For today, I have prepared many interesting topics. We will learn about how we calculate time-dependent effects in Alpine Bridge. So basically, we're going to talk about creep, shrinkage, and relaxation. And of course, what is also important that we know how we set up these effects, how different parameters affect the calculation, and all of the different settings that are combined here, and then that we can deliver a good result. So, but first of all, let's take a look at the content. We have 4 topics. Basically, we have 4 points on our agenda. First of all, a short introduction. We will briefly explain a bit more into detail what we're going to talk about today, what kind of time-dependent effects do we calculate, what they basically are. And once we have done this, we are going to the definition of the time-dependent analysis, and we will really go step by step through all the parameters, through all the settings, through all the definitions that basically affect the time-dependent calculation. In the third point of our agenda, we will take a look at an example that is coming in the upcoming version, and this is a verification example according to Eurocode, and this one is done specifically for creep and shrinkage calculation. So in this third point, we will take a look at the calculation procedure, at the hand calculations, and then compare them to the results that we have calculated with Alpine Bridge. At the end, of course, of the conclusion, we will just do a short recap of everything we have heard today. So let's get started. First of all, as I said, the introduction, and the things that we're going to talk about today is what is time-dependent analysis in Alpine Bridge. Basically, we have 3 topics here. This is creep, shrinkage, and relaxation. We will see how it's defined, how all the parameters work together, how we define, for example, the infinite creep, how material properties affect the time-dependent calculation. And of course, when we are doing this, we also need to know how we define the construction schedule, how we define different tasks. So what does these tasks do? What do they mean? And how do they affect the calculation? And of course, here, if we have, for example, some task-specific parameters, we're also going to take a look at that. And as I already mentioned, the new verification example for creep and shrinkage, which again, is not yet in the software, but will be delivered in the October version. Okay, so let's take a look at the time-dependent effects that we have in Alpine Bridge. First of all, this is creep. And creep is the effect due to which concrete undergoes continuous deformation under sustained loading, which is applied for a considerable time. The next effect that is also really important for us is shrinkage. And what does this mean? This drying of concrete is basically independent of applied loads. And since it causes some contractions in the concrete, it will cause also tensile stresses. And in case this gets restrained, these tensile stresses can cause cracking of concrete. And last but not least is a material property of pre-stressing steel. This is relaxation, and it behaves inversely to concrete creeping. It basically describes the reduction of existing stress at constantly applied material strain. And these are the main effects that we calculate in Alpine Bridge. So now we know what we are going to talk about today. Now let's go a bit more deeper into the matter. So let's talk about the definition of time-dependent analysis. First of all, let's get an overview. What affects time-dependent analysis in our software? First of all, we are talking about material values. So we have concrete, which has the effects of creeping and shrinkage. And then we have pre-stressing steel, which, as we already mentioned, has the effect of relaxation. This is one thing that affects it. The next one is the construction schedule. So, of course, it depends how we set the construction stage up. It depends on our calculation tasks. From the setup of the construction stage, I specifically mean when we do activation of some elements, because this will affect our structural system. There will be changes in the structural system, and we will get additional creep steps. The next one is it basically falls into the construction schedule definition, but is a bit more detailed. These are the environmental factors. Because we will see, once we go a bit more into the detail, we will see that we can define a construction schedule in Alpine Bridge, and this construction schedule can have several phases beneath it. And these phases have the possibility to set the environmental factors, which are in our case the relative humidity and the environmental temperature. And we allow that, for example, different phases can have different values for temperature and the humidity. And this basically, if we imagine that we start building a bridge, let's say in January, where we will have different temperatures, and we say that the bridge, the construction will be finished then, let's say in fall. In the same year, we will go through different transitions of seasons, and then because of that we will have different environmental factors, and this is what we can consider in our construction schedule definition. Of course, we also consider the application of loads that happen in the construction, let's say in the time of the construction. If we will apply some additional loads, it's not only activation of different objects, but also the application of loads, which would then also result in additional creep steps. Okay, so now let's go step by step a bit more into detail. First of all, material values that affect it. So this is now for concrete, and we can consider two different types of concrete. So first of all, we have normal strength concrete, or we also consider then for these time-dependent effects also high-performance concretes or ultra-high performance concretes. You can see on the right side, you can see the properties window of the material of the concrete. For this we have an online database that in every project you can also download all your material definitions, but then once in the project you will be able to modify these basic material values. But what we are going to talk about today, what interests us in this point, are the values for cement content, silicate content, and cement class. So let's take a look. Cement class, this is the class of hardening of concrete, and we distinguish between three different classes. So we have rapid, normal, or slow, and this is also defined by the number that we put in here. So for example, in this example that we have with the number 1, we have cement class 1, which means rapid hardening. The next one is cement content, which basically applies only for high performance concretes or ultra high performance concretes. That's why in this case we didn't consider it and we set the value just to 0. And of course the same goes for silicate content, which also applies only for high performance concretes and ultra high performance concretes. Next one is the pre-stressing steel. Also on the right side in this properties window we see the basic material values that have been imported into the project from our online material database. And we're going to talk about here about the values that affect the relaxation calculation. And of course, if we take a look at these materials, we have one important definition, and this is the relaxation class, where we also define this with numbers from 1 to 3, where the number 1 means the lowest relaxation of the steel, and then 3 would be the highest. And of course, this determines then the time-dependent pre-stressing losses from material values. So this is about the material values. The next, what we have mentioned, are environmental factors. And as I already have been talking about a bit, these environmental factors are defined in the construction schedule. But now on the right side, we can see this property window, and this is not the construction schedule property window, but it's basically the different phases that we define inside them. And this is one window. This is the property window of the phase that we have defined, and there we already see a submenu basically where you can input the parameters for the relative humidity and the temperature under creep and shrinkage. And of course, as already mentioned, different values according to phases can be defined. Okay, so this is about the environmental factors. And the next step is the construction schedule. So here also, how we define, how we set up the construction schedule, how is our bridge going to be built, what different phases we're going to have, when we are going to activate an element, are we going to have some simulation of some construction loads, everything will affect the time-dependent analysis if it's relevant. We will go a bit more into detail later because I have also prepared a short live example where we are going to define a construction schedule together. So if you go a bit deeper into the construction schedule, as I've been talking, what basically happens here in the construction schedule, we define how the structure is going to be built and we define the loads. We either define the loads after the final creep and shrinkage calculation has been done, or we define them during the construction, for example. And basically what explains how our new creep steps are applied or defined, we basically see very good on this diagram at the bottom left. So just maybe quickly explain here, if we are in an initial time of t0, we will apply a load to the structure. This will, of course, at the same moment, it will result in an elastic strain. And after the time passes, we also get some creep strain. Once we get to a certain point of to a certain point in time, like here, we decide that we're going to remove the load. And of course, what happens is some kind of elastic recovery, and then along the time axis, we get also some creep recovery, but we are still left with this permanent deformation. And this is why that we also correctly consider creeping and creeping of creeping in our calculations. The next thing, which also holds some of the parameters that we need to define for the time-dependent analysis, are the calculation options. So if you take a look, if you already know, if you have been using Alpine Bridge for analysis, you will know that you have the possibility to do the auto-generate calculation task. So this will automatically generate for you these basic load cases like self-weight, superimposed dead loads, pre-stressing, creep and shrinkage, and then the total summation load case. So this is one thing that we can set here. So for example, if we take a look at creep and shrinkage, this means that we will have a load case called CS, which basically stands for creep shrinkage, but it also includes the relaxation effects if we have them calculated. And of course, a summation load case when, for example, a relevant event happens, like for example, we activate a stage, we get a new creep step, we will have another load case at this point in time. We will also see this a bit more detailed later. And of course, a summation load case, what happened till this point. What is also important here is that we can set the duration of infinite creep in days. So in this example, we have set it to 36 and 500 days. So to do a short recap, now we have been going through these basic parameters. So we've been talking about material values, about concrete, about relaxation, about environmental factors, about some basic settings, and then about calculation options. But now let's take a look at an example. So here we have an example on a pre-stressed concrete bridge. You may know this example. This is our, let's say, most documented example in the software. It's the first one you will see. It comes with an extensive PDF where you have a step-by-step guide how to model this bridge, how to analyze it, and with all the explanations that you need to get started. So that's why we're going to look at this bridge. You have it in your software. You can then open it up and just check for yourself. Quickly about the bridge, we have a concrete bridge with 3 spans. The lengths of the spans are 45 meters, then the middle one is 65, and the last one is 45 meters again. The bridge is supported in 4 positions, so start at the station 45, station 110, and at the end. And of course, it's a hollow box cross-section. So this is about the geometrical properties of the bridge. Now let's take a look what we have defined here from the material definitions point of view. So we have concrete, and as you can see already on the right side, we have the concrete strength class of C35 through 45. So this means it doesn't classify as high performance concrete or ultra high performance concrete. That's why we didn't set any cement content or any silicate content. And in this example, we have set the cement class 1, which stands for rapid hardening. This is all that is important for us now at this point for this definition of materials for the concrete for this example. And of course, the next one is then pre-stressing steel. And in this case, we also see all the basic material values that we're using in this project. But here we have defined the relaxation class of 2, which translates to normal relaxation levels. And this affects then the relaxation losses in pre-stressing tendons. So this is from the material point of view. Then we are going to talk about a bit about the construction schedule. We can see the whole construction schedule on the right side, but for us, for the time-dependent effects, what is now important are the first 5 phases. And here we're talking about the construction stage 1, construction stage 2, which is the span 1, then the stage 3, stage 4, and the superimposed dead loads, where we basically apply the loads of the sidewalks on the structure. But we will see this also how it's done live. Of course, this example also comes with different load applications like settlement, temperature, braking, but this part we will not consider in this webinar because it's not important for us. Okay, so let's take a look at the construction schedule. What we will see in the construction schedule are 3 main tasks that we will be working with. So first of all, it's the concrete task, and this concrete task does the activation of concrete members, calculates the self-weight, and starts the calculation of creep and shrinkage. On the right side, you see a schematic representation how this concrete task is set up. Basically, the concrete task is a container, and inside it, it hides 2 more tasks. So this is pour and hardening of concrete. It comes with some parameters that we need to set. So we either set the start and end date, or we set the duration, so start date and duration, and this is then the end date is automatically calculated. There is also one additional factor, and this is the shrink parameter, which says when we are going to start the calculation of shrinkage. So we can set an offset, for example, from the start date. So let's say the whole duration of this task is 21 days, but if we set the D-shrink, for example, to 6, it means that we will start the calculation of shrinkage on day 15. I mean, on day 6, but then it will be calculated for 15 days, not for 21. We will go a bit more into detail on the next slides, how these tasks are set up. The next important task is in subtask. So this is the activation of structural supports. If you take a look at this Gantt diagram that we see on the right side, we have, for example, a schematic representation how a bridge is being built, for example. So we start here with our first concrete task. If you remember, we have a start date and then we have a duration. If we would have set, for example, the D-shrink parameter, we will also have an offset where the shrinkage starts. But what happens after this task is complete? The self-weight load case is calculated and this part of the structure is activated. And at this point in time, we activate the supports. Now we start calculating the creepage, shrinkage, and relaxation until we do another change in the structure. And here we have another change in the structural system because we decided to activate another element. We have activated additional supports and we have activated some pre-stressing tendons. And this is where we're going to see also in our results, we are going to see another creep and shrinkage load case, another creep step, because this is a relevant event that changes the calculation from this point forwards. And then again, we start calculating the creepage, shrinkage, relaxation, and again, we have a change in the structural system, and so on and so on. We will see all these different results also then live, and we will see how they are basically generated phase by phase. And of course, forgot to mention here also what is important, the tension task, which basically evaluates the tendon stressing, calculates pre-stressing load case, and establishes the bond between the tendons and the cross-section. So this is just a brief overview. Now let's go a bit more into detail what a task basically does. First of all, the concrete task. And as you see on the left side, but first of all, before I start explaining, you can find these explanations if you will go to the construction schedule and make use of our F1 help. You will get all these same definitions there, and you can take a look at them whenever you need them. So the concrete task basically consists of two tasks. This is pouring the concrete and hardening of concrete. Then we have some automatic generated calculation task, which is the ins concrete, the calculation of the self-weight and calculation of the creep. And this ins conc is basically installing the concrete element. And what it basically does, it activates the member, it calculates the self-weight and starts the creep and shrinkage calculation. This task comes with additional parameters. First of all, parameters from construction, so start day and duration. So we need to know how long it's going to take and what the age of the concrete will be when it's activated. And as we already mentioned, we have the de-shrink parameter, which represents the age of the concrete at the beginning of shrinkage. Then the next one, this is not basically a very specific container task. This is just a task that activates the bearings and springs. We are calling here, we are talking about the install task. So install supports. And this task is important for us because if you're talking about creep and shrinkage calculation, specifically about creep, once we have a change in the structural system, this will mostly result from activating a member or basically activating additional supports which will change the structural system and change the distribution of internal forces on our structure. And of course, last but not least, is the construction tension task, which consists of 4 different subtasks, which is installing the ducts, installing the tendons, stressing and grouting. And this basically, what it does, it evaluates the tendon stressing, which we define in the tendon stressing procedure. We calculate the pre-stressing load case and establish the bond between the tendons and the cross-section. So let's take a look at the results. Time-dependent results are stored in the CS load case, which stands for creep and shrinkage, but it also includes the relaxation effects. As already mentioned, for every relevant event in the construction schedule, a new CS and a CS sum load case is created. For example, if we get a new activation, if we get a change in the structural system, or we decide to apply a load during construction. Then, once we get to the results, we also have 2 different results representation types, which we need to cover. And we can take a look at the forces that are related to concrete section only. And in this case, the tendon areas are not considered. And the result pretension, so only the resulting forces on the concrete are displayed. So what we remove from the concrete, from the tendon, is not considered here. So we only just basically consider the concrete section. And then we have forces that are related to the resisting section. And in this case, the idealized cross-section is considered, which displays the forces on the cross-section, tendons and grouting concrete. So these are the 2 important result representations that we show. So this has been briefly about this example. Now I would like to jump into the software and show how it's done. So for this, I will open up Alpine Bridge. You can already see my project being prepared. And if I take a look, this is now basically this getting started example that I've been talking about. If you don't know where to find it, I will show you now. You can go just simply click on this Alpine icon to enter the backstage menu. And if you go to examples under modeling and analysis, you will have the getting started example. And here you can access the manual, which is, as already mentioned, an extensive PDF document. Okay, so let's take a look what we're going to do. I have no construction schedule yet defined, but we will do it together. But first of all, take a look at what of the settings are already set. First of all, we need to define the standard. And if you haven't done so, when you created the project, you can always do it once you're already inside the project. So for this, you go to options, and on the top left side, you will have the project settings. and here we can find, as this third title is standard, then I can define EN, and you will see which standards are implemented. For example, here we can say, for example, ASHTO or ENTOS means that they're fully implemented, but we also support creep and shrinkage calculation for the JTG standard for China or KBDC for Korea. Of course, these standards also often come with national annexes. That's why we are also working on implementing the relevant standards. We will of course cover all of them that you see here in some point in time, but at this stage you will see in a bold font written which standards are implemented. So for example, we have the national annex for Germany, Spain, France, and this is it. And basically, if we consider a national annex, if it's implemented, it will also, if it contains any, let's say, additional definitions how the creep and shrinkage is calculated, it will also be considered in our calculations. Okay, so the next thing that we can take a look at is the materials that we have inside. We have concrete types with the cement class defined, which one, as we said, translates to rapid hardening of concrete. And we have no cement content and no silicate content because it doesn't classify as ultra high performance concretes. Of course, then also pre-stressing steel, where we have a relaxation class with the number 2. This means normal relaxation. But now it's time that we see how a construction schedule is defined. For this, I will go to constructions, right click, create a new construction, and I will set the first phase, which I will call construction stage 1, and this will be for the piers, for example. And once I click on this construction stage, you will see already on the right side the creep and shrinkage values that you can define on the phase level. And this is the relative humidity, which is by default set to 75%, and the temperature, which is by default set to 20 degrees. So this one is for piers. And here, what we are going to need, is we are going to need two tasks. We will need the concrete task and we will need the activation of supports. Because in this first example, we are going to activate the piers. So I will take the concrete task. You see here you already get the message that if you press F1, you will get more information about this task, and there you will also get access to these tables, which all the definitions of all the different subtasks that are defined inside this container task. So let's start this one. Sorry, oh, it's already there. Okay. So I have it here, the concrete task, and as mentioned previously, I need to set the duration here. And let's say the duration of this task will be 21 days, so I can already set it here, 21 days. And after this 21 days of constructing, I will activate the supports. So for this, I will go back to construction and I will take the inst sub task, which automatically takes, if it's defined after this one, automatically takes over the start date. Okay, so now how do we define the assemblies? We can either click here on assemblies and use our filters, for example, to just select piers, and I can select the pier here, press enter, have the first one, and then also the second one. And if I click on the task, I will see at the bottom right, I will see those two elements being activated in this task. There's also another way, which I prefer to use, for example, that if I know, okay, I only need the bearings, basically the soil support to support the piers, and I want to put them inside, I can go to the geometry tree and say, okay, this is pier 1, pier 2, and just drop them inside. And so our first task is now defined. We can start, for example, already the calculation now, and we can take a look at the results. So let's go to calculation. Let's set auto-generate calculation tasks, structure analysis, and here we take a look at this additional calculation options. So everything looks good. We can leave everything checked on. So we will calculate self-weight, superimpose dead loads. Pre-stressing will come in the next phases, but we can leave it on here. and creep and shrinkage. So by default, the duration of infinite creep is set to basically 100 years, so 36,500 days, and we can just go here with the default settings. So let's calculate this. I think we will get some warnings. Yes, we get some warnings, but those are not really important. They just remind us that we didn't activate some of the elements, but we will do this in the next step, so don't worry about it. So we see now, if we go to the analysis model, if we go to results, for example, we see all kinds of results being calculated. But for now, this is now those steps that are calculated and for the infinite creep are not now the focus, what we're trying to see. But we know that on the day 21, we have activated the peers. That's why I will just take a look for this load case. And here I have, no, this is not 21, sorry, it's, I think it's this one. So this is when the structure is being activated. And of course, if we take a look at additional steps, we also see, for example, how those values then change. For example, here at the bottom left, we will see how this creep calculation and effects of shrinkage on this peer works along the time, working its way to the final date of creeping. So let's continue now with the definition of our construction schedule, and we will define a new phase. And what we can do now is we can create a new phase, which we'll call construction stage 2, like this, and this will be span 1, like this, and maybe we just create another copy, and this will be construction stage 3, like this, and span. This is the second span, so the middle one. I will just create another copy, so I don't need to rewrite all the names. So this is the construction stage 4 with span 3, like this. And what we are also going to have is one additional stage, which is the STL load case. So basically here we are going to activate or create the load cases that are basically the superimposed dead loads, and those will also affect, because they happen during the construction time, they will also affect the creep and shrinkage calculation. So let's go with OK, like this. One additional thing that we have in properties I forgot to mention is that, for example, if you click on a certain phase, you will see a start day, for example, a global start day, but you also have to set this option to final. And this means that it basically does not affect the creep calculation. For example, the loads won't affect the creep calculation because they happen after the duration of the infinite creep. So after the infinite creep has been calculated, we apply these loads if we set a stage to final. Okay, so let's go to our stage, construction stage 2 for this first span. And here we are also going to have a concrete task, we are going to have an install task, and we are going to have a tension task. And I'll just set the start date here to 36, for example, like this. And this one will have a duration of 14 days. I will set it here to 49, and also the tensioning to 49, like this. And now, for this first span, we're going to activate only part of the structure. That's why we go first to concrete, and I will click on assembly. I will make use of my filter, so only girders, and I will start by the station 0 and go to station, I think, 50. And for example, if I didn't define it correctly, I can always click here on the assembly at the bottom left and then set another station to 55, for example. Okay, what we need to do is, from the support, we need to activate the abutment here at the beginning, and because this bridge rests on bearings, we also need to activate the bearings below here. So let's do this, go back to the geometry, and we have those bearings 1, 1 and 1, 2, and the abutment 1, and I can just drag them inside here. So this looks good, we see them highlighted here, everything is fine. Of course, the next thing that comes now is applying tendon stressing, and we will activate the tendons here. And for this, we have already prepared this. If you take a look at the example, once you're going to the geometry, you will see that you have tendons already defined to different phases for the left and the right side. And now for this first phase, we can take the phase 1 left and phase 1 right tendons and just drag them inside. And if we click again, we see that we have activated the correct tendons. So let's calculate this and take a look at the results. If I go to the results tab, you will see that, for example, if we go back to span 1, we have an event. So something changes in our structural system on day 49. We will have another load case on day 49. And here it is, for example, that we have the creep and shrinkage calculation on day 49. This basically depends what we would like to show here, or we take a look at the summation load case on day 49 for the creep and shrinkage. And we see, because this has been only activated here, we don't see basically any effects here, but we see some effects, for example, here already on our pier level, and we see already a deformation that is happening to our structural element here on the left pier and also on the right pier. Of course, this element was creeping till now only from its own weight, but now also the weight of the superstructure is applied to it, and this will also affect the additional creep and shrinkage calculation. But let's continue with the definition. We have 2 more spans to go. So I will go to span 2. And for this one, of course, I will also need the same tasks as previously. So let's go to construction. Let's create a concrete task. Set the start date to 65 here, for example, duration of 14 days, and I will need to activate the supports and do the tensioning. So concrete here, once we will click on the assembly, we see what has already been activated. Let's maybe make this a bit bigger, and I will now activate the second span. So this will go from here where the first phase ends, and I will just go to here to the station 120. So this is this stage. Of course, we need to activate the bearings. I will go to geometry, structure, and the bearings 2.1 and 2.2, like this. And if we go to tensioning, we will have on the tendons, we have phase 2, the second phase for left and right side, and we can just drag them inside. Let's run the calculation. If we have done something wrong, if we've got something to define, we will get some errors here, and we will get a log message to see what we have forgot or what is the problem here. But for now, everything looks good. We still get some warnings because still some parts of the structure are not have not been yet activated. So if you take a look at the results, we have now another point in time. So day 78. We get some additional effects to the structure, and of course this is only the activation of this part. We have now activated the second span, so from somewhere here to here, but we already see that something on our result level is already happening in the first span, so we get some kind of deformations already in the structure. So let's continue with the last span, and then our bridge has been built. So if we go to the construction stage 4 for span 3, I will have a concrete task, and this will have a start date of 94, again a duration of 14 days, and of course I need to activate the supports, and I need to do, of course, the tensioning. Here what I'm going to activate is the remaining part of the structure, so go from here till the end. Of course, of the supports, what I need to activate is the last abutment. So let's go to structure and just pull the last abutment inside. And if we go to tensioning, we are still missing the last 2 phases. So phase 3 left and phase 3 right, like this. So this is the whole structure. We have taken a look at the results now before for every stage. Now let's maybe skip viewing the results at this point and just define the superimposed dead load. But we see that this also then affects the creep and shrinkage calculation. And then we'll take a look at the final results from our construction definition. So I go now to the superimposed dead load case, or basically phase, which happens, which will start on the day 227. And for this, I won't define any of the tasks here, but I will define a load case. And this load case will be named STL. And of course, I will add it to the summation load case for the superimposed dead load. Press OK. And now I'm going to define 5 loads inside. So this will be basically vertical line loads. Of course, they require an assembly. So let's start with this. Let's go. Select from start till end. So this is the peer. Of course, we should set a start date. So this will be 127. And what we need to do is, because now in this one, we would like to define the roadway. We would like to apply the load of the roadway that is being built in the bridge, and we have it in our actual 3D model, not just a simulation of the load. For this, we need to define the uload parameter, and this is what this is. I will show you on the cross-section level. If you take a look here, we see that, for example, this parts of the structure are defined in a green color, and here we are talking about structure unit loads. So those elements get only activated as a load on the structure and are not considered in the stiffness matrix. And that's why they have another color, so that we can distinguish them. And to define them in some point in time of the construction, we just need to type in the number of this structure unit load. So for example, we have 5 and 6, 3 and 4, and the number 2 for the roadway. So just so that you know where I'm getting these numbers from, but you will see just in a moment, once I type in the number 2, this is now okay, confirmed. And if I click back again, I see this highlighted in a green color, so this means that this roadway is being activated here. So I will just copy this one with assemblies and continue with the right sidewalk. So number 3. And if I switch, you see now only this right sidewalk is being activated here. And copy once more with assemblies, number 4. And of course copy with assemblies, then I will go with number 5. And again, copy with assemblies, number 6. And now we can go through them and visually check if everything looks correct. So here we have the left sidewalk and then the left barrier. So this is it from the construction stage definition. I can go and take a look now at the results that I have calculated. So we see no warnings anymore because all of the elements that are considered in our analytical model have now been activated. And of course, take a look at the results. So we see that we have now many different load cases, and you see, as I was already mentioning, showing in the diagram, that we activate or create additional tasks, additional creep steps that are being introduced here, where there was a relevant event, like activating, for example, part of the structure, or if we continue to the next stage where the second stage was activated, or then, of course, when the last stage was activated, we can have then different result representations for our bridge. And of course, what I have also mentioned is the STL load case, for example, that we basically have also an event for the creep and shrinkage load case at the day 127, because some additional loads have been applied. And of course, for this also the creep and shrinkage calculation will change for its foreseeable duration. Of course, then we also introduce some additional steps until the infinite creep calculation. I was also mentioning the switch between forces that are related to resisting section only. We can do this here in the action bar for the forces, where we can switch between forces that are related to a resisting section and forces that relate basically to concrete section only. So this has been from the live demo. Now I suggest we jump back in into our presentation, where we are going to take a look at the last point, basically last important point that we have on our schedule, and this is the verification example according to Eurocode. So I will just go briefly through this. You will have a full documented PDF attached to the example in the October version, where you can really take a look at every formula that we have used. how the calculations compare to Alpine Bridge, and you will see that we get pretty good results, basically almost the same results with hand calculations and what we get from Alpine Bridge. First of all, it's a simplified example. So this is a simple T-beam concrete girder with a single span with a total length of 15 meters. It's supported at both ends, and we calculate creep and shrinkage according to Eurocode. Let's talk about analytical properties. So we have concrete with the hardening class C 30 through 37. Cement class is 2, so this means normal hardening. Hardening. And we didn't input any actual tendons, but we simulate pre-stressing loaders by applying an actual force of 500 kilonewtons in the COG. To also get some kind of creep effects, because we didn't consider the self-weight, we apply the load on day 100 and remove it on day 350. So let's take a look at about the calculation. The calculation of displacements is done in 3 stages. So first of all, we do it before loading, where we have an effective duration of 93 days. Then after loading with an effective duration of 251 days, and the displacement after 15 years. So calculated days, this means 5,475 days. First of all, what we have done the calculation of the geometrical properties. So from our geometrical properties like length and areas, we have calculated the HO parameter, and then the KH value has been interpolated using linear interpolation from the tables provided by the standard. Of course, we calculate also the effective duration, and this is basically just a formula where we subtract basically from the point that we have, for example, T 351 days, we subtract the value of 100 days. So how did we calculate the shrinkage calculation? I think I don't want to go too much into formulas now, but I will just briefly go what kind of formulas have we used for calculation of the beta RH value, then calculation for the beta DS values. So these are just formulas that are being taken from the standard and then basically compared to what we get out of Alpine Bridge. So of course, once we calculate the beta factors, we calculate the drying shrinkage strain, and of course we calculate the autogenous shrinkage strain. And of course, if we compare the results to Alpine Bridge, we get on the bottom left, we see basically the shrinkage calculation that we get from Alpine Bridge, and on the right side we see the results that we have calculated by our hand calculation. So we see we are pretty spot on with this result, so we get kind of the same results compared to our hand calculations and compared to the Alpine Bridge example. Of course, the same we have done for creep. We are calculating the factors according to Eurocode, so beta H, beta C factors. Of course, we calculate also the creep coefficient and calculation of creep strain. And basically then to calculate the creep displacement, we need to calculate the stresses caused by the acting force from the following equation, as we see on the right side. So I'm just not trying to go too much into detail here, because it's just formulas from the standard. But what interests us most are the results representation, which we also get a perfect match here with the results calculated on the right side by hand calculations, and at the bottom here in this table we see the results that have been taken from Alpine Bridge. So let's come to our conclusion. What did we learn today? What did we see today? So we have seen properties and settings that affect the time-dependent analysis. So we have been talking about material values, what affects concrete, what values from concrete affect the calculation, what values from pre-stressing steel. We have seen the important tasks in our construction schedule, how we define the construction schedule, how we can set different parameters for each phase. So how does this affect? How, for example, we see the results depending on how our structural system changes, that we introduce new load cases on this specific date where something has happened to the structure, where there was a relevant event. And at the end, of course, also the verification example, which you can take a closer look at it in the upcoming release. This was it for today. Thank you for joining the webinar. Hopefully you have seen something new. Maybe you have learned something new how to do this in Alpen Bridge. Maybe you have now, hopefully you have now a deeper understanding of how we calculate time-dependent effects. Thank you again for joining, and see you at our next webinar. Goodbye.